Sorry about that. I accidentally had some technical issues with the video. So as I was saying in the video before it stopped, we are talking about LDA, and LDA can be used for various purposes. But whenever we use LDA, it has to be we use it for alkylation, but the alkylation will always occur on the least sub side of the molecule. And so you have to make sure that whenever you're doing this, do not forget that aspect of this reaction. Okay, so there are other ways to alkylate, and one of these ways is something that you're actually quite familiar with. And so one other way is something called using Stork synthesis. Right? So Stork synthesis. So what Stork synthesis is whenever we use, okay, so something that you know, right? So whenever we use a a secondary amine, so this is a secondary amine, and carbonyl H plus, we will get the, right? So we will get the enamine. So the enamine looks like this. And you have to remember it forms the most sub double bond here. And so the way this enamine works, we can use this enamine as a means to attack some electrophile. It can be any electrophile, right? And usually it's alkylation, right? So we can use this, and what I want to do is I want to step away for a moment and show everyone how similar this looks to what we have in the enol form. So the enol form, right, in the tautomerism, right, it looks like this, right? We have some carbonyl, and then I have like a double bond, and I have my R groups, whatever is there. And the way that we can do the reaction, I've shown you us using the carbonyl when it's has a negative charge here, right? This is just one form. This is like the resonance form. One way we can do this as well is this oxygen donating its lone pair in, and this coming out and attacking some electrophile. And so this is the way this works as well. And so this looks very similar. We have something that can donate density, electron density inwards, and push out this density to attack as a nucleophile. And so the way this works is this is going to come in. And you have to know this. You have to know this. You have to know what this looks like. And so let's say I have some RBR. This will come out and attack. Okay? And what we'll get at the first step, you have to know what this looks like. So we'll get this nitrogen, this two R groups. Okay? Let's call this R prime just so we can differentiate. It's now going to be positive, right? And if you're confused why it's positive, nitrogen in neutral state has 3 bonds and 1 lone pair. Now it has 4 bonds. So 4 bonds is the positive form of nitrogen. Now, this carbon right here is going to have the addition of the R prime. And so you need to know this, and you need to be able to draw this out. This is very important, and she will take up points if you do not show this. Okay? And then the last remaining step, if I so wish to, well, we do wish to get back the carbonyl, right? Because my purpose in the beginning was to alpha alkylate this carbonyl structure. So right now I don't have a carbonyl, obviously. So the way I can get back my carbonyl is to do H3O plus, right? And we know that H3O plus does the reverse. It reverses both the formation of the imine and the enamine. And so I will get back my carbonyl, blah, 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 and I have my R prime. So this is how this works. And this is the general easy mechanism for the way this works. Remember, it's very helpful if you understand that how this happens. right? Nitrogen donates its lone electron density inwards, and the bromine attacks the alkyl halide or any kind of electrophile. Um, one takeaway I also want to share is that um, whenever we have, it relates to this as well, but whenever we have the keto and the enol forms in the presence of an aqueous solution, right, which is almost all the time, so in the presence of an acid or a base, um, but, having a base or acid does not necessarily mean that we have an aqueous solution, but in the case that we have an acid or base where it's aqueous, the keto form is always more stable than the enol form. Okay, so what you need to know is that the keto form is always the preferred form of the tautomerism, right? So that's just something that's very important that you need to know. And this has to do with the oxygen and and the nitrogen here donating their lone pair density inwards and kicking this double bond out and promoting the formation of the keto form or the double bonded form to the electronegative group. All right, so let's move on. So that was Stork synthesis. All right, and so now we're going to start getting into the actual, nitty-gritty stuff. So the nitty-gritty stuff is now where we're going to move away from using LDA and we're going to be using things like, okay, what you'll always use, NaOET, ETOH. Okay, and so essentially the difference between this and LDA is that these are not strong. Okay, these are not strong. It's not a strong base, and so what that means is that let's say I start with 100 of these, maybe I'll get 40. Okay, maybe I'll get 40 where they're in this form, with the negative charge. That's what, and you'll see why this is important. So what you need to know is that whenever we do this, right, what will happen whenever we use ketones, aldehydes, esters, right, they're always going to self-attack themselves first, okay? And the reason for this is why we use this in the first place. So whenever we use ketones or aldehydes, this is called, right, so ketones, okay? And whenever we use an ester, oh, bring this over here, right? So these are two of the just basic reaction types that we have over here. They work the same way, just they work with different functional groups and they'll produce different looking products. And so here I have a ketone, right? This could be a ketone, could be an aldehyde. It just depends if I have the hydrogen, but they work the same way. And so let's talk about why this happens. So I have a ketone. I have a base, it's decently strong, but it's not that strong. And so it's going to promote the formation of the deprotonation of the alpha hydrogen to this carbonyl. And so because it's not strong, right, it's not going to give me 100% of this forming. And so what will happen is I'll get some of these. So let's say I get like 40 of these out of the 100, so 40%, and then I'll get a lot of these still hanging around, right? So I'll have this interplay, this will have some equilibrium going on here, right? But I will not have a sharp, like a large formation of this majority product. I'm going to have a mix of both. And so this is important because we want to have this condensation reaction, right? And so the condensation reaction is the merging of two molecules. That is a condensation. And so the reason why this self-attacks is, as I just explained, I have some of these guys with the negative charge, and I have some of these guys which are the electrophile. So now I have both a nucleophile and an electrophile, and they happen to be the same molecule, just different forms of the same molecule. One is deprotonated, one is not. And so this will attack itself, right? And so what we get, okay, so I'm gonna put this up here. So what we get, we have the original one. I'm gonna draw that carbon, and then this carbon is attached to another carbon which has has this O minus group on it, and it has 2 carbon groups that were on it. And so this is what we have. And then after this step, right, because I have this ETOH, this will, this will get protonated. Okay, so plus H plus, okay? And so this is just going to get protonated. It's not an H plus reaction, I'm just saying that hydrogen from this is going to be added here. And so we will have this alcohol that forms. Right, so the final product of this reaction, right, so the final product of this reaction is this. All right, and so one thing that we can do to take this step further, right, one thing you need to differentiate is the addition of heat. And so if I add heat either over here, or I can have it as separate steps. She may have it differently. She may have it as separate, or she may have them all together. It doesn't matter. If the heat is present with this, what will happen is we'll have a dehydration step. And so essentially, you'll have to show the mechanism. You'll have to know the mechanism for this, but I don't think I have the time to show all the mechanism right now. But essentially what will happen is we can take the base, and we can what we can do is we can deprotonate a hydrogen that is right here. Okay, so this hydrogen right here. All right, and so this hydrogen can be deprotonated, and when we deprotonate it, right, using the the base that we have over here, right, we will get this structure. I guess I'll just show some parts of the mechanism. We'll talk about it very briefly. We'll get this, we have this, we have this, right? And so we get this minus right here. Okay? So the first thing you have to do when this is for mechanism part of the exam, okay? You have to show this negative charge going up into the carbonyl and then coming back down, and essentially what it does, it'll kick off this OH group. And so it goes up in the carbonyl, show that, then coming back down, and then when it comes down, it forms a double bond right here and kicks off the OH group. Okay, so what we get in the product is we get this carbonyl. Okay, I get this. And so what we call this is the alpha Okay, so this is the alpha beta unsaturated product. This is alpha, this is the beta. Okay, and notice how the alcohol is on the beta carbon, right? To the final product. Okay, and so this is what we get. But this is only whenever we have heat. Heat promotes the dehydration. This process is dehydration. Okay, and this is the base catalyzed dehydration. You can also have acid catalyzed, works similarly, but not too important right now. We usually use the base to do so. Okay, so you need to know how to do the ketone aldehyde aldol. This is called aldol condensation. This is the condensated product. This is the dehydrated product. Okay, so very important. Now let's look at the Claisen product. So I'm just gonna take all this. All right, so got all that out of the way. All right, now let's look at Claisen. Claisen, I said, is with esters. So let's grab an ester right here. And all right. So we have this Claisen, right? This is going to be Claisen. And so the difference between the Claisen and the aldol is the fact that esters have this OR leaving group, right? This can function as a leaving group, as we've seen before. And so the first thing that happens is that we have the formation of, with the base, the removal of the acidic alpha hydrogen. So we have this. And just like before, we don't have the complete conversion of this into the deprotonated, conjugate base. All right? And so we have this guy. This guy is going to attack itself. When it does so, okay, this is what we get, right? And you must always show this whenever you have any OAT, E2H, and if you have a ketone, aldehyde, or ester, you must always first show the condensed product. That is the first thing that happens. Okay, and so I need to show this. Okay, and so from off of this carbon, I attacked this carbon. Okay, so this went up. This is this carbon, this went up, and over here I have this group, and I have this group, right? Right now I have what we call the unstable tetrahedral complex, okay? And so this does not stay. Instead of getting protonated, this comes back down and kicks off this OR group. And so what we get, right, you should already be familiar with this mechanism, right? And so what we get is this very interesting group right here. And so this is the product of this reaction, okay? So this reaction produces this structure, and it's a unique structure. It's called the beta like beta oxo whatever, or basically you have a carbonyl at the beta position. Okay, and these are referred to as, okay, this is its own type of molecule. It's malonic, whatever. They have different, didn't spell it correctly. Malon. So what we have here is the malonic ester. Okay, malonic is just whenever we have these dicarbonyl structure. All right, and this is a very special structure because at the end of this reaction, right, before we finish, before I can move on to step 2 of let's say she had this in a reaction, before I can move on to step 2, what I have to know is that this is still in the presence of this acidic basic environment, right? And so I have some base still floating around, and essentially in the beginning I started off with deprotonation of this alpha hydrogen acid, right? And so this hydrogen was acidic. And let's say, I'm being vague here, I'm not being accurate. This had a pK value of 9, right? Had a pK value of 9. And we said that this hydrogen is acidic because it can resonate with this carbonyl structure. This carbonyl structure gives it stability, right? It gives it the ability for this negative charge that forms the conjugate base to be stabilized. And so that makes something acidic because an acid's strength, an acidic hydrogen's ability to be acidic, is solely dependent on how stable the conjugate base that forms, right? So the more stable the conjugate base, the more resonance structures, or the more electronegative the atom that takes on the charge, or so on and so forth, right? The more acidic it is. And so therefore, what I'm trying to make you think is now I formed a product in a basic environment that now has 2 carbonyl structures. So now it has double, right, the resonance. So now, let's say this hydrogen right here, there are hydrogens right here. These hydrogens in between the carbonyls now have, a pK of 9. Let's say it went down to pK of 8. And so now I went from something from being less acidic to more acidic. And so this will all be in the form, actually, instead of the protonated form at first. So the product that you will get, right, is this. So this is what you would have to show. This is the end of this mechanism of this reaction. You have to show this is the product. And to get the protonated product, I have to use, acidic condition, right, or H plus. And so this will give me my final product. Okay. All right. So here's Claisen. Here's Claisen. All right. And now what we need to know. What we need to know. So some things we need to talk about. So alkylation of beta-dicarbonyl compounds. So she's using it here. So it says more acidic than monocarbonyl compounds. This is what I have just illustrated, right? And what we need to know is that these compounds, right? So there's 3 of them. There is the one that has 2 esters on each side, right? They're both esters. There's one where there's 1 ester, and then there's one where they're both ketones. Okay? But regardless, whenever you have a dicarbonyl compound, beta-dicarbonyl compound, what you need to know is that these compounds, like let's say this was the first molecule used in this NaOH reaction, it will not perform the self-attack. Okay, so dicarbonyl okay, so I'm just gonna drag this over here. All right, beta-dicarbonyl molecules will not self-attack. Right? So they will not self-attack each other. And so they will not do this whole Claisen or Aldol like condensation. They will just attack whatever electrophile is present in the reaction. Okay? So that's just something very important to know. All right, now that covers up the Aldol and Claisen, right? So now we have one more thing, right? We have something called decarboxylation. So decarboxylation is the process by which whenever I form a dicarbonyl product that has either an ester group carboxylic acid group or any other group, okay, the most important thing you'll see is that we have to have a carboxylic acid, okay? So the rule for decarboxylation is that you have 1 carbonyl, and then on the beta position, alpha, and on the beta position, we have a carboxylic acid, right? And so we can use a variety of different things. And I'm just going to show some examples, right? All of these things can be made into the carboxylic acid. And this is made, right? Decarboxylation occurs under the conditions of H3O plus and high heat, and specifically 180 degrees Celsius. So under H3 plus and heat, essentially this group will be turned into a carboxylic acid. This group, we learned the carboxylation of nitrile groups, right? You learned that with H3 plus and heat, we can turn a nitrile into a carboxylic acid. We learned that H3 plus, heat, we can turn an ester into a carboxylic acid. We learned, with H3 plus and heat, let's say we had this structure. We had carbonyl, and then we had anhydride. With HCO plus, we can turn the anhydride into a carboxylic acid. All right, so on and so forth. So anything that can be turned into a carboxylic acid will undergo decarboxylation. And so what does a decarboxylated product look like? It essentially looks like if I completely removed, right? I completely cut off this, took off a CO2. Okay, it's CO2. So I take off that group and I'm left with just this carbon. So I'm left with this 1, 2, 3. And this is carbon 4, and carbon 4 becomes incorporated into CO2. And this is what I'm left with in the product. And so you need to know at the end of Claisen, right? At the end of Claisen, I can perform a decarboxylation step that removes that OR group. Okay? So that's what we need to know. And so now we can just let's show, right? She shows it in her notes, but let's just show how this all works. Okay? So let's say I have carbonyl, right? And we have the carboxylic acid. That's what we need. Right? So essentially what happens is this very weird mechanism. So what we do is to summarize mechanism, you draw in one step, it's just a transition state. We show this bond coming out and grabbing this hydrogen. Okay? Then we show this bond going in and forming a bond right here. And then we show this bond right here going in right here. And what we get at first, we get the enol. Okay? This is the product. This is the enol. And then we just formed CO2, which is a gas that can bubble out, right? CO2 gas. And so we're left with the enol form. And if you remember what I said earlier, we said the enol form under, acidic or aqueous conditions will tautomerize to the keto form. It's more stable. And so what will happen is we take this H3O plus. This is going to donate inwards. This is going to come out, grab a hydrogen. Sorry, my handwriting is so garbage. And so we get this, okay? All right, so this comes out and grabs this hydrogen. This is neutral now, but now we have this. And all that's left is, deep protonation using water, right? And then we get the carbonyl. All right, and this is our answer. Okay, so this is the decarboxylation mechanism that, this is generally what you need to understand. And so take any, dicarbonyl, beta-dicarbonyl, and if the beta-dicarbonyl is part of a ester or a carboxylic acid, or even if maybe not, it wasn't any of those things, maybe it was a nitrile, right? Anything that can eventually form a carboxylic acid in the presence of H3O plus and high heat, that's something that we can work with. So this will completely remove a carbon and its oxygens evaporate off CO2, and we'll be left with this carbon right here and the rest of the molecule as demonstrated. All right. So that's it for that. That's it for the aldol and the Claisen reactions. Okay. So now what I want to turn our attention to is something called Michael. All right, Michael reactions. Now the Michael reactions, she said, would not be on this exam. However, I do not trust that she may, she may not entirely include it. I don't care. Last exam, she put enamine on the mechanism. That screwed a lot of people over, even though it wasn't supposed to be on the exam. So I want everyone to understand Michael, all right? At least to some degree. All right, so here's the book. I'm just going to use the book to save some time. And what we have here is the Michael reaction, right? The Michael reaction consists of the of two of a malonic compound and a conjugated compound. Okay, and so it consists of a nucleophile of an acceptor, right, and a donor. A nucleophile and electrophile. Electrophile is a acceptor, nucleophile is a donor. And so the Michael reaction is going to be split up into two pieces. So we have acceptor and we have donors. And so Michael donors, aside from the first two is a cuprate, organocuprate, right? The Gelman reagent, right? Lithium cuprate. And then the second one is the enamine. So basically, your Stork, right? Then the rest are these beta-diketone, beta-ketoester, beta-ketonitrile, beta-nitroketone. Basically, your malonic looking like structures. So your two carbonyls. And essentially, we're going to be using these guys because they form good nucleophiles, right? This hydrogen that is in between the two withdrawing groups, so a ketone and some other withdrawing group, right, as seen, is going to be deprotonated much better under the presence of NaOH, ETOH, to get this negative charge. And this will be the nucleophile that will attack the acceptors. The acceptors always are a conjugated system. So it's always a double bond. So basically they're dienophiles. A double bond with an aldehyde, double bond with a ketone, double bond with an ester, double bond with amide, double bond with a nitrile, and double bond with a nitro group. And so the essential mechanism for this reaction is we will have, very simply, okay, plus some double bond structure, okay, I want to draw it like that. Some double bond structure that's conjugated with a carbonyl or some withdrawing group under the presence of, our NaOH, ETOH, right? Strong acid, strong base mixture. And this is going to deprotonate this acidic hydrogen right here. So it's going to take off this hydrogen and give us this negative charge. This negative charge, like we said, this malonic compounds, right? These dicarbonyls or these compounds do not self-attack. So we won't have to worry about this attacking itself. So we will have this coming and attacking right here. And this will come out, come over here, and this will go up. Alright? So essentially we have this conjugated system. And so because I have a conjugated system with a withdrawing group, this allows this carbon right here to be a electrophilic site. And so this will accept a electron, a nucleophilic attack, a new bond formation, because this can be pushed out into the withdrawing group, right? And so it's because of that, right? And so the product of this first step, right? This is a very basic Michael reaction. The product of this first step yields me this. So I draw this, right? And then I show this bond, right? So I bond it to this carbon. So I have to add 1, 2, 3, 4. So 1, 2, 3, 4. All right. On carbon 3, right? That is where I have between carbon 2 and carbon 3, that's where I have my double bond. And then on carbon 3, I have a O minus. All right. And so once I have this, what do I form? Well, I form, this becomes the OH group, right? Right. Essentially, I don't even need to demonstrate that. Essentially, like I said, we're going to have a tautomerism. So we form basically an enol or enolate. This is going to come back down, right? Before we're done with the forming the product, this is going to come back down, and then this is going to take off hydrogen, right? So, sorry, this is supposed to be, this is 1, this is 2. So this line should be right here. My bad. Right? So it should be right here. Okay, this is 1, this is 2, this is 3, this is 4, as seen. Alright, so between 2 and 3, that's where the double bond should be. So this is going to come push this down, and this is going to come out and attack this hydrogen. Alright, and what we get, right, we get the keto form back. So I get this carbonyl and this one, right, our original structure. I then get, right, so 1, 2, 3, carbon 3, I have my carbonyl. And so here is our answer. Okay, so here is the answer. So the way you know you have a microproduct is if you count from one carbonyl to another, you will always get 5 total carbons, including the carbonyls. And so this is the microproduct. Right? So it works the same way with other groups. Only thing to note, right, I'm going to show the book again. Only thing to note is that if I use in my Michael donor, if I use either a ester or a nitrile, I will be able to perform decarboxylation later on because I have either an ester or a nitrile, and if I introduce H3O plus 180 degrees, I will be able to remove one of these groups because I have the right dicarbonyl structure, right? So if it was like this, and it started out like this, and if I perform H3 plus 180 degrees, this obviously would remove this whole group. Okay, so that is all you need to know for this exam. I wish everyone the best of luck, and I will be trying to post a video of me going through an exam tomorrow. Please study your reactions and know your mechanisms well. She will not mess around with this exam. She will try to screw you guys over on the thing, especially because she has been upset with people missing class. So make sure you try to go over her notes, try to understand the main mechanisms, and really make sure that you are solid on that material. All right, best of luck, guys, and